Yo, welcome back to the live stream of 2 months syllabus completion challenge, day 7. And yes, nobody's gonna watch, of course, because I'm a YouTuber who's just, not that famous at all. So let's just start the studies today. Today, we are gonna do pure physics. What I mean by pure physics is I think most of the day will go by through the physics because I have to prepare for my physics test. And yes, it's one chapter actually, known as work, energy, and power. Also, 1 minute, I gotta add one contact. It's really important for me to do that. I just hope that I don't leak it, or else I'm cooked. Okay, wait a minute, guys. I mean, this looks pure safe. Do you mind if I keep it here? Nice, okay. I can keep it here. I can. Let's just do it. Um, I'm gonna add the contact. Okay. How do I? Oh wait. Got it. Got it. Let me just add one contact. I wanna do that part first. Okay. Hmm. Okay, I added the contact. This does not look bad. Okay. That was kind of nice. Wait a minute. All right, let's start. I'm gonna unmute my mic just for because this live stream I thought like let's put it as non-quiet mode so that we can actually just interact a bit. I mean, I don't want to interact, but let's just do it. Let's just do it. Work, energy, and power. That's in chapter five. So what is work in physics? Work then is basically the amount of force that you apply on the body in order to displace it. That is known as work done, of course. And I'm also gonna practice a bit. Yeah, I gotta practice. So wait a minute. I just gotta stop that out. You know what? I can't actually. I don't want to leak my friend's number. Sorry, I just can't do that. It will cause a lot of problems. So I have to blur that out. I mean, blur that out meaning that I have to shade that out for now. And yeah, the country code. I can't show the country code. All right, let's just start now. I hope you can't see anything now. Yeah, you can't now because the numbers are cut out. All right, let's start. Let's start. We're gonna cook. So first of all, we have studied about work. What's the formula of work then? It is force vector dot s vector. Now, why is work then a scalar quantity? First of all, it is known as a scalar quantity, but why is it so? We see that there are two vectors in its formula. That is, W is equal to F vector dot S vector. Now, what we know is that force and displacement are both vector quantities. When they get multiplied, we're basically doing the dot product, and dot product is also known as scalar product. Since the scalar product of force and displacement is always going to be a scalar, that is work done, you just need to know the fact that both the vectors that when they multiply and which the multiplication taking place as dot product or scalar product, then that will be known as the scalar quantity. We already know that. Nice. Now, talking about this, work done's unit is joules, and in CGS units, it could be called as erg or ERG actually, erg. And what is the value of 1 joule? It's 10 raised to 7 erg. Let's go, my guy. And sometimes we need to have some basic idea of what is going to be there. So suppose there is an object. I'm going to take this object, I'm going to displace it through some force, but my force is basically acting upwards, but the displacement is going through this, meaning that there is an angle between them. It does not always be in you see there is not only a situation where you see force and displacement going in the same direction. It could be in different directions too. So yeah, technically I can say that the direction taken here to here basically, that will okay, I didn't show it properly, but I know that I'm just studying and this is not quite notes. Of course, I'm so sorry if I'm disturbing you guys. I thought like nobody's watching my stream. Let's just do it, my guys. So yeah, what do I mean here is that there is an upward slope. There is suppose this is the force actually, and this is displacement. You see that there is an angle created between the force and displacement, and let's name that angle as theta. And since we are naming the angle as theta, we can also say that the body got displaced because displacement vector is also there, and this theta could be lesser than 90 degrees because we just have the angle I just showed you is an acute angle. It's less than 90 degrees, of course. So if I write this at sorry, if I write theta lesser than 90, I would say that this is an acute angle. Yes, that's true, it's an acute angle. But there is another point to it. What is the another point? What is that freaking point? Freak. I didn't swear. Okay. Yeah. Suppose this is your f vector. F cos theta may act here, and F sine theta, because our vector resolution takes place here, F sine theta. Upward force also happens because that's what is basically, guys. And yeah, S also takes place. What I can refer from here is that um, lesser than 90 degrees is basically positive work done. The amount of work done by a force in which the direction of the force and displacement is the force vector, and the angle between the force vector and the displacement vector is less than 90 degrees, or an acute angle, we know that it is a positive work done. Since it is a positive work done, we can say that it is basically very, very important for us to know that it is very important. Okay, just saw my accent. Yeah. I can speak in an American accent, my guy, or I can speak in Indian accent also. You don't know? I can speak in Indian too. Really, my guy? Oh my god, that is actually crazy to know that no people, no people thinking about this. Oh, this is my another version of English where I don't apply grammar actually. And this is another version that I usually apply sometimes in mainly of my videos. If you don't know, let's just talk about the nature of work done. Now, the nature of work, or wait a minute, the constant force is also given here. Well, let's just read this. The work done by constant force is measured as the product of component of force and the direction of displacement and magnitude of displacement. Of course, displacement and force are literal vector quantities. You need to know that. Right, guys? Yeah, yes, you got it right. Positive work done. Okay. And then we got zero work done, which has basically two cases, and negative work done. What should I go through this? Let's just go through this. If the angle between F vector and S vector is an acute angle, work is said to be positive. In this case, cos theta is positive and therefore work becomes positive. When a body is vertically downwards, work done by the force of gravity on the body is positive. This is because the displacement of body is in the same direction of force of gravity. If I talk about negative work, it is the work done by force and becomes negative because the angle between the force vector and the displacement vector may be greater than 90 degrees, basically an obtuse angle, or it could be a straight line that is 180 degrees, right? Of course, it could be that too. Uh, since it could be an obtuse angle, and from what I had referred uh, from, is that negative work done is actually gonna have these two vectors in like literal opposite directions actually. So I can say that this one, and the cos theta, yeah, the cos theta value is also varying here. You see, cos theta lesser than 90 will go somewhere around from 1 to 0, but 90 to 180 it will go from 0 to negative 1, meaning that there will be negative values. Okay, so yeah, that is also a true part. So from 90 to 180, that's a fact actually. That theta will be here, W work done is going to be done, and that's how we can explain this and justify that. This work done is negative because the force acting on the body is actually on another part of the side, whereas the displacement vector is just some other just in a straight line going through and getting displaced off. Now, if I talk about the zero protein, it has two cases. The first case is that the force is exerted on the body. The force is exerted on the body in which it does not displace, in which it doesn't displace. And then you have got another of yours of work done. Wait a minute, guys, I just got reminded of something else. Could you please wait? 1 minute, guys. There's a small thing going on. 1 minute. Okay. What is going on? Wait, guys. Can you stop, please? Oh my God. Hello. Just stop for a minute. Oh my God. Sorry, guys. I'm actually. You feel like I'm getting distracted, but it's important actually for me to do because I have to also cover the next physics topic. That's why. Based on that, I need it. So yes. Hmm. Oh wait a minute. Today's 8th October. Tomorrow is 9th October. Day after tomorrow. Yeah, that day. It's 10th October. Uh, yeah, you know it. You got it. Ha ha ha. I know. You got it. Uh, I'm just stupid. That's it. Okay. So work done being zero there's another reason that if force vector is f vector is perpendicular to s vector, then work done might be zero. Why? Because um, theta value will be 90 degrees, of course, and if we know exactly the product of work done, it's f vector dot s vector. Now it's a scalar product. I can write it as fs cos theta. Okay, that's a thing actually, and based on that, I can actually write cos 90. That will be, I guess. Wait a minute, guys. Fs cos 90. Cos 90 will be zero. So that will give us zero. So work done is zero. Easy part. Okay, let me just read this up. If the work done by force becomes negative when the angle becomes between F vector and S vector is greater than 90, work done by the force of gravity is in lifting the body vertically upwards is negative. This is because of the displacement of body is opposite to the direction of the force. Of course. Now there's three examples for this. Oh my god. For zero work done, that's crazy. Okay, I think I can explain this. Suppose when I push the wall. I don't have a wall nearby. I cannot show it actually, sadly. Suppose I'm gonna push this thing. Okay, this is displacing. Oh my god, that's not so good. That's stupid. Suppose, wait a minute, I'm just gonna move a bit aside and I'm gonna try putting in a force on this. I'm exerting a force. You can see that I'm exerting a force. Not only that, but this does not displace. Yeah, I'm exerting the force. You can literally hear my voice crackling out, meaning that I'm literally exerting the force, and you can see that this does not displace. Since force is acting upon it, and still the displacement doesn't act, does not get displaced. The object does not displace. Then we will say that the work done by that force is zero, because we need the body to be displaced. But this cannot always be the condition. Sometimes even some objects that are moving in that are in motion, they are displacing, but still we sometimes say that they are actually zero. Why? Because in some cases, suppose let's just think about this as sun. This is earth, or I will say this is earth. This is moon. Okay, the moon is orbiting or revolving around the earth. Now our moon is revolving, orbiting around the earth. We know that what is going on here is that moon is orbiting around it. We see that this actually revolves around it. Now since this revolves around the planet earth, we have the idea of saying that this work done is what? How? Well, pen. Yeah, I'm showing it with pen. Well, just imagine that it's or, my finger. Just imagine it doesn't move. Okay. So you see, gravitational force is actually giving us the centripetal force. What is going exactly on here is that when we see the displacement exactly when there is no centripetal force, the moon just wants to go in a tangential straight direction, meaning that it tends to move this side, but it cannot, so it moves like this. Yeah, suppose I'm going to take my headphones off, I'm going to swing this up, and you will see the centripetal force that I'm applying, okay? Yeah. So as you can see, oh, wait a minute. I just don't want to hurt myself. So, oh my god, this is difficult. Okay, so you can see that I'm actually putting this headphones in centripetal force, and they're revolving around the center. And if I drop them off, they will actually move around that direction itself. You just saw the headphones going through this direction, and that is the tangential direction. If there was no centripetal force that around the moon, then it would not have had happened. Meaning that the Earth is basically, is first of all giving us the gravitational force, and even on the moon. The moon reason why is revolving around Earth and does not fall upon the Earth is because it does not fall because that it moves along the tangential direction. So what I can say is that I can draw the diagram here and I can explain it to you. First of all, suppose this is gonna be your Earth. This I'm not sure whether it will be a perfect circle, but yeah, I got it. And I'm gonna wait a minute, guys. Wait a minute. Okay. And this is gonna be your. Yep, nobody is. And yep, this is your moon. Yeah, that is moon right there. You see what is going on here? Suppose when the moon comes here, the displacement is somewhere going here, but the force is actually acting here. It's the attractive force. That's what is going on. Yeah, so it's perpendicular. Similarly, you can see this path too. The path of this here is tangential path, meaning the displacement is going through this side. But again, the force of attraction wants the moon to come this side towards the Earth, and this is perpendicular. Now, since the angle theta is perpendicular, we know that cos 90 will be 0, and therefore work done is 0. Got it, guys? And there's another thing is that it string tied at the end. Uh, uh, um, sorry, the stone tied at the end of the string is spinned around is revolved around the center of the string, which gets the provided tension force. This tension force acts upon towards the center of the string, and therefore the center and acts as a centripetal necessary centripetal force. So we get the idea, but the displacement of the stone is in a tangential direction, and therefore it causes the revolt. And I know it looks very weird because you see that. it does not actually get displaced. I mean, it gets kind of displaced honestly, but then you see that the displacement vector is actually not even getting followed out. It's just trying to go to this path as an form of impending motion, but it goes through a if and it goes through a curve that is arc, and then it completes a one revolution, and that's all. That's again and again and again and again and again without getting. Now, we know that force can always not be constant. This is because if we see in our daily lives, force can. There are some things that always not be constant. Actually, if you have seen a car on a traffic road, you know that the car is of course not be moving in a uniform motion, or else the car is basically doomed because there's a really high chance he might crash up on something. And uniform motion meaning that not much slow and not much faster. I mean non-uniform motion. It could be at rest, it could go, it could stop, it could to go, anything. It could be anything. But yeah, uniform motion is just like that constant speed that is taking place at very different times of intervals. But that is not upon the non-uniform motion. So similarly, forces can act upon too. You see, we are the way we exert the force on any object is actually not accurate. We do not actually put a constant force. There may be there's a high chance that we actually apply a variable force. And why do we even want to find a variable force? Well, variable force means that force value may change from different time intervals. Yeah, that's important too. I had to drink water, my bad. Okay, never mind. Deep breath, please. Wait. Why did I just say deep breath? It's not even there in physics, but yet there in chemistry. Now let's just talk about work done by variable force. Variable force, first of all, what is variable force? We will have to explain that first of all. Can I? Yes, of course. Force, different values of force seen. Wait, in equal intervals of time. Seen in many time intervals. Okay. Hmm. Suppose this is convert to. Okay, got. I got. अच्छा अब बॉडी की डायग्राम मान लो अरे यार एक लाइन है ये एक कोलिनियर लाइन है मतलब इसमें 3 पॉइंट्स हैं ओ ए और बी मैंने बोला था कि बॉडी डिस्प्लेस हुआ है मैंने बोला था बॉडी डिस्प्लेस हुआ मैं क्या बोलना चाहता हूँ कि यहाँ पर ये दो डिस्प्लेसमेंट क्या होता है तो बताता हूँ फर्स्ट ऑफ ऑल तो पहले इसमें अंदर देना चलो यहाँ पर मैंने ये भी मेंशन किया था कि छोटा सा वैल्यू दिया था दैट इज डी एस वेक्टर एफ वेक्टर यहाँ पर मान लो एक्ट अप हो रहा है इसके ऊपर ऐसा ये एफ वेक्टर बात बात में सो ओके तो यहाँ हिंदी मोड ब्रो मुझे भी हिंदी आती है let's just start off okay guys let's just start now now we know that S this will be S1 vector where this is the displacement of the body. No way, the ink just ran out that quick. Oh, this is my second pen. Okay, S2 vector. You see, why are we actually doing this? I'm gonna explain you why. First of all, we need to know the displacement. First of all, we need to have the idea. Originally, we can actually refer this to as A to B, and we can actually do this. But then we need to also mention the another displacement. Actually, that's why. And this one is a very small displacement. Why? Because we're going to use this as another one. The reason why we just took another displacement and another displacement as a lower and higher limit is because we are going to use integration, and the integral sign can be also have limits. It's not going to be like an no. I don't want to put it as an infinite integral sign. I want to put it as a limit integral sign, meaning that if I actually put this, first of all, a very small amount of work has been done in order to move this up. So f dot ds vector if I put integral on both the sides, integral on both sides, then we can say that this dw is equal to this is going to be SASB, and this is going to be no, let's not put that up. We're going to just put this SASB. That's what I can say here of and F dot f vector dot ds vector, and that's how you can actually explain the whole thing. Now dw, if you take the integral of dw, you will get w. So you'll get the total work done here. So that's easy to way to find it out. So SB will be your higher integral, and sorry, higher limit, and SA will be the lower limit, and that's how you're gonna find the variable force, the work done by variable force. And that's a really good way to actually do it. So if I try to make a graph out of it, graph out of it, um, stating that there is the force and displacement graph. This is your force. This is your displacement. Force is going to be very like variable. So it's gonna be a curve, and yes, the displacement, this is going to be your displacement of the body that takes place, and this small thing I'm going to actually uh, carve out the area of this, is going to be ds. Okay, I just basically found the work done, that's dw by the way, but if I put the limits, I'm going to actually get the whole value for it, that is w value. So W, if I just say what is basically what will be the value here, A, B, C, D, and if I try to write the W or the work done area, this is see, the area of this is basically, of this thingy is basically F into S. Okay, oh sorry, that's gonna be dot product, my bad. F dot S vector, and that is basically of this shape is going to be basically like multiplying both stuff. So f vector dot s vector, and therefore we are going to get a w is equal to f vector dot s vector, and that is scalar quantity right there. That is area of abcd, area of abcd. Now we're going to talk about some forces which are really important to learn and work done, and it may be useful later on. That is conservative force and non-conservative forces. What are conservative forces and non-conservative forces? Conservative forces are those types of forces where we have seen in some parts of our life that actually the total work done. I mean, we haven't observed it, but yeah, we have seen their kinds of experiments, their practical analysis. Like, you're gonna basically draw the pen, it will come down. So you're not gonna draw that. I mean, you're gonna take this and throw it up, and it'll come down. See? Ouch! It comes down. Yep. So that's how you can say that you can explain it to this, and that is actually interesting, amazing word right there. So, uh, what I mean here is that there are two types: conservative and non-conservative. These are really easy to define. So, the main points we need to know for this is easy. I'm just going to write it right here. Mm, so that you'll get the idea. And we're going to do the derivation. Of course, there will be derivations. I don't want to skip any derivation, as it is really important for us to like do this. We're going to first of all start off with our potential energy derivation, and then we're going to derive the elastic potential, the derivation, sorry, kinetic energy derivation. It's very easy. You can easily solve this and you can get the answer. But suppose if I need for gravitational potential, it's also easy. You're gonna just put, work done is equal to F into S. F is mg and S is height, and you're gonna put mgh, and boom, you got the gravitational potential formula. Very very easy. And by the way, um, work done most of the times it could be negative because you're basically lifting up the body. So negative work done is actually taking place, but you take preferring the magnitude um, of the potential energy. Energy is a scalar quantity. We take it as a magnitude, right? So it's gonna just be mgh. That's what we know. Now, elastic potential energy of the spring. That's not only spring. It could be elastic potential energy. We have studied that potential energy is basically the energy amount of energy to change an object that acts upon the body due to the virtue of its position and to change its change of configuration. The virtue of position basically it talks about the gravitational potential energy, and the change of configuration talks about the elastic potential energy. And there's another type of elastic and inelastic property, that is the collisions that we're going to learn. It's very easy, known as elastic collision and inelastic collision. It will take out the topic of conservation of momentum. It's very easy to define and all that stuff. But for now, what I really could think of is that it's better to first of all start off with Learning the energy part, right? Let's just start. Yes, you got. Oh wait, no, wait. Conservative forces. How could I forget that? The conservative forces. Yeah, we gotta know how to do the conservative forces. Yeah. We're gonna start off that and all that takes us to matter of with all the subjects. We're gonna know that word. Uh oh. Uh oh. Uh oh. This is bad. What Hello? Are you there? Say, please. Oh, wait a minute. Oh no. Oh. Hey yo. Oh, wait a minute. Okay. I'm I don't know what I just they said music later on this Oh god, God. You, Okay, never mind. Yes, you can hear me. Let's go, you can hear me now. The weird, like a weird. Work energy and power electron. Wow, that's a lot what that was. Friction. See, see that is a very small topic. Circular motion. Damn, damn. How is it that crazy? I mean, what motion in plane is just vast. Just saying that motion in plane is basically a chapter where it has vectors and circular motion combined. So big that oh my god, that is so big. Oh my god. No way I didn't know that. How? Then you say that laws of motion. I mean, yeah, laws of motion also has friction. That's sensible. So how many chapters does it have overall? I can say four chapters. Does not include units and measurements, but it's fine. It's fine. But yes, this is actually crazy. I like it. I like it. We're gonna apply this. We're gonna use this. We're gonna actually study physics for the vectors, and we're gonna go through a lot of stuff. But 'Dang, I like that. I like that. You really was. 90. It's crazy. Wow. Anyways, 1 minute, guys. Oh, wait a minute. No way. Oh, okay, never mind, never mind. Oh my god. Damn. यहाँ
राइट राइस ठंडा हो जरा राइट नहीं 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 मैं
Okay, go. Guys, I will come back soon. Okay, I might have to end this early. I don't like to end it like this, but unfortunately, I have to. Oh, I hate this, but I'll come back as fast as possible. So sorry, guys. Bye.